Okay, so we're going to now move over to a new topic, and this week we'll be talking about relativistic effects. Um, so it's going to be similar to the kind of things we've been talking about electric fields, magnetic fields, the forces and how particles move, their dynamics. But now we're going to explicitly take into account any relativistic effect. So if the particles are moving close to the speed of light, we want to know what the extra corrections are. I assume that you're all familiar with special relativity. We won't be using general relativity in this course, so it's only going to be special relativity. And I do know that you come from different backgrounds, so I'm going to do a little bit of recap in this video, but I'm going to end with some concept which you probably not heard of, even if you're physics students, which is the aberration of light. So let's do a quick recap. So there are two postulates of special relativity. And the first one is that the laws of physics are the same in all inertial frames. Okay, and what is an inertial frame? It's a frame where the velocity of a particle doesn't change as long as there's no force applied on the particle. Okay, so if you're in an inertial frame, then let's say you're co-moving with other particles in an inertial frame, then it just means that if some particle is not acted by a force, then you don't see that its velocity is changing. So then you know you're in an inertial frame. An example of a non-inertial frame is basically a rotating body. So if you're like an observer who's just sitting on top and riding on top of a rotating body like the Earth, then you do see that in your frame the velocity of particles change without any force being applied on it. And the classic example of that is a Foucault pendulum, right? So if you have a pendulum that is swinging, and then as the Earth rotates, you actually see the plane of the pendulum shift as a function of time. And so you know you're not in an inertial frame. Anyway, so we're going to be talking about transformations within inertial frames. So suffice it to say that the first postulate is that the physical laws of force equal to mass into acceleration, that kind of stuff, the Maxwell's equations, all of that, they're going to be same in non-inertial frames. That doesn't mean that every measurement you do is going to be the same in all inertial frames. So you and your friend can be in two different inertial frames. Your friend measures some electric field and you can measure a different electric field. Okay. The only thing this is saying is that Maxwell's equations are satisfied for you and for your friend. Even though you might measure different electric fields, it'll turn out that you'll also measure different magnetic fields. So, in the end, the equations are satisfied for both of you individually. The second postulate is that the maximum speed of information transfer is the speed of light. So nothing goes faster than the speed of light, and that information cannot be transferred faster than the speed of light. It also, this should also bring forth in your mind that photons are going to travel at the speed of light in all frames, but other particles are going to travel at speeds less than the speed of light. So you cannot carry any information faster than the photons can carry them. And the photons are moving at the speed of light, which is a constant in all inertial frames. Okay, so with these two postulates, it turns out that you can actually derive a huge amount of results just from these two simple postulates. And that's the beauty of these postulates. So let's get started. So we're going to talk about events. And an event is something that happens at a given space at a given time. Okay, so I'm just going to call event 1 happening at XYZ at time t1, x1, y1, z1 at time t1. And I'm going to call an event 2, which happens at x2, y2, z2. Those are the Cartesian coordinates at time t2. And I want to construct what is called an interval between the events. Okay, and you can think of this analogous to the distance between 2 points in Cartesian space. So I'm going to construct the interval as c, the speed of light, which is a constant, times delta t square minus of the Cartesian distance between the points. Okay, and this choice is deliberate. So the last 3 terms here are just the Cartesian distance, and this term here is just the time difference, but it's scaled with the speed of light. So the main point of doing it this way is to basically make, if event 1 and event 2 consist of a photon being emitted and photon being absorbed, so photon moving from one location to the other, the way this is constructed is is that for a photon, this thing is going to go to 0. Okay, so for light, that quantity is 0 in all inertial frames. Oh, by the way, this should be a c square. I apologize. Otherwise, it's dimensionally incorrect. So for light, that is going to be 0. For other particles, it's going to be some factor, right? It's not going to be 0 because nothing is traveling as fast as light. It's going to be some factor alpha here. And you know, you can now use that factor to basically relate this interval between two frames. So let's say you're in frame 1 and then your friend is in frame 2, and you measure an interval delta s square in your frame, and your friend measures an interval delta s prime in the primed frame. And then now I'm asking the question, how do I relate this kind of distance between two events? Now, if we know that we are both talking about light, both of you measure 0, right? So what happens if you're measuring not light, but some other particles, right? So if you're measuring some event which is not connected with the light propagating between one point to the other. So one thing you can say is that because space, we also assume that space is homogeneous and isotropic, this function which goes from one frame to the other, it cannot depend on the direction or the coordinates of the frame, right? So it cannot depend on which way the frame is oriented or, you know, some location in the frame. It can't depend on x, y, z, t basically, right? This, otherwise space is not going to be homogeneous. Then the transformation would depend on where you are in space. So we know that this can't be a function of x, y, z, or t. The other thing we know is that this alpha can only be a function of the relative velocity between the two frames, because that is the only different thing between the two frames. And that comes from the first postulate, right? The laws of physics have to be the same in all the frames. So any difference you measure in this interval has to just depend on that relative velocity between the two frames. And if this alpha is not dependent only on the relative velocity, but other physical parameters, then you'll not be able to satisfy postulate 1. You'll end up with different laws in different frames. Okay, so what can we say about alpha? You can say a whole lot with, you know, with just this postulate. So just imagine that you have 3 frames. One frame is k, okay? Another frame is k1, and k1 is moving with velocity v1 with respect to k, and k2 is another frame, the third frame, moving at velocity v2 with respect to k. Okay, so I'm going to write again the equations for the interval. So ds square is the interval in frame k. It's going to now depend on the interval measured by your friend in frame k1 times this scalar value alpha, which is now going to depend on v1, because v1 is the velocity difference between the two frames. Similarly, ds square is going to depend on ds2 square. So now let's say you have another friend who's in this frame k2, and your friend is making some measurements, and your friend comes back and says, I measured ds2, and then you say, oh, well, whatever I measured should be alpha times, you know, ds2, and now, you know, that function alpha is going to return a scalar, but the argument you're going to use is v2, because your friend was moving at velocity v2 with respect to your frame. Now, all of that is fine, straightforward. Something really interesting happens if you say, well, what if your two friends talk to each other, right? The two people in frame k1 and k2, they're going to come up with this equation. They're going to say ds1 square is alpha times v1 minus v2, and notice that I basically took the magnitude of it, because again, it cannot depend on the direction. If space is homogeneous, you know, this result cannot depend on the direction of v1 and v2. That would make space inhomogeneous, and we assume that space is homogeneous here. And you know, they're going to come up with, you know, some equation like this, right? Now, sorry, this should be ds2 square, not ds12. Yeah. Now you have 3 equations. You know, you can you know, divide one by the other, and, you know, try to find some relationship between some relationship that tells you what that function alpha is. So what you end up with is alpha of v2 divided by alpha of v1 is equal to alpha of v1 minus v2, right? Magnitude, and that just comes from these 3 equations. Now this should be true for any v1, v2. I could choose any vector as, okay, smaller than the speed of light, but I could choose any orientation, any speed lower than the speed of light, and this thing must be true. Now, that's a tall ask, right? I mean, you're saying that I can literally choose any vector I want here. They can have any direction. So their magnitude actually depends on the direction between the angle between the two vectors. The only way you're going to satisfy all of this is alpha just has to be 1, right? I mean, if alpha is not 1, if you make alpha any function of velocity, I can come up with vectors which will violate this equality, right? So alpha has to be equal to 1, which means that if two frames are inertial frames, and then moving with respect to one another, then the intervals have to be the same between the two frames, right? And this interval is 0 for light, and for other particles, it can be some other value, but it has to be the same. Now, this is kind of trivial if you're just talking about non-relativistic stuff, like let's say you're just talking about distance between 2 points, right? So let's say I forget for a moment, I'm going to forget this term here. Again, this has to be c squared, sorry. I just take this term, right? That is just the distance between 2 points. Yeah, I mean, then this statement is pretty trivial, right? You're saying that, let's say I give you 2 points, I measure the distance between the 2 points. Your friend is in a moving frame, your friend measures the distance between 2 points, forget special relativity and all of that. You're just saying that the distance between the 2 points have to be the same. Now, once you introduce this term here, it makes a whole world of difference. Now it means that you actually won't even agree on the distance between 2 points. You're not going to agree on measurement of time because everything is now coupled. The only thing that remains the same is that interval, right? So I can play around with, there's some function which you're going to find, which you need to transform transform, let's say, position between the two frames or velocities between the two frames because of this coupling, because now time and space are coupled. So I need to think of this as some kind of 4-dimensional space where there are 3 spatial dimensions and 1 c times time, right? Some kind of a 4th spatial dimension. It's really a time dimension, but you can always multiply it by c and get to the same units. Now, the easiest way to think about this equation here of the interval being the same in the two frames is to think about rotations in 4-dimensional space. And again, the analogy to 3 dimensions is useful here. So if you just had 3 dimensions, and then you say that I need some transformation to go from one frame to the other, but the distance between the 2 points have to be preserved in this transformation. Well, the most general form of the transformation is a rotation, right? So you can take your coordinate axis, you can rotate it by some angle, and any which way you want to rotate it, any which way you want to do these rotations, you'll always end up with the property that the distance between 2 points is not going to change if you just rotate your coordinate axis. Now we're talking about a rotation in 4 dimensions, right? So we're going to now say that the most general transformation is some kind of a rotation in 4 dimensions. So what does it look like? So let's just fix some axes so our life becomes simpler. Let's consider a scenario where there are 2 frames and the relative velocity between them is only along the x-axis. Okay, and in language of special relativity, you say that there is a boost along x-axis, a Lorentz boost along x-axis. That means that nothing is going to change on the y and the z dimension. So you're going to your transformation equations now become simpler. So here's the interval in one frame, here's the interval in the other frame, and these 2 intervals have to be the same, right? And so you can say, what is the most general solution to this problem of rotation, right? This is just a problem of rotation from one frame to the other, and what is the most general rotation that can preserve this property. Now, if that minus sign weren't there, you could just say that that rotation is a simple Cartesian rotation, right? So you would say that if this were a plus sign here, you would say, wow, well, this is a 2-dimensional plane where you have dx on one axis, c times dt on the other axis, and I'm just going to rotate the one coordinate frame with respect to the other, and this is just the distance between 2 points. Or in this case, I've taken the origins to be the same. So this would just be distance from the origin. And the distance from the origin is not going to change if I just rotate the coordinate axis. I'm not stretching the axis, right? I'm not doing any such things which violate this distance constraint. Okay, I'm not doing any stretching. I'm not doing any sharing. I'm not bending the 2-dimensional plane. I'm just taking the plane and rotating it and calling it a different frame, right? So it doesn't change the distance, but now we have a minus sign here. So the algebra completely changes. And so the most general solution, you can express it in terms of hyperbolic trigonometric function. So you have x equal to x prime cos hyperbolic psi, where psi is the angle of rotation between the two planes, two frames, sorry, plus c t prime sine hyperbolic. Now again, if this were a plus sign, you would just, instead of hyperbolic, you would just use normal trigonometric functions, and yeah, then you would do x square plus c square t square is going to just end up being x prime square plus c square t prime square. Once you put hyperbolic here, there's an extra negative sign. So this kind of transformation, you use hyperbolic functions to get this kind of transformation. Now, you can get a few other properties here. I mean, you can always work with hyperbolic functions, but it turns out that it has a much simpler geometric form. And you can derive the geometric form. You can put x prime equal to 0, and you basically get x equal to ct prime times sine hyperbolic psi from the first equation. And then from the second equation, you just get ct equal to ct prime cos hyperbolic psi. So I've just gotten rid of this term by saying x prime equal to 0. And what does it tell you? So x divided by ct must be tan hyperbolic of psi, right? I'm just dividing these two. Now, so this just gives you an equation for tan hyperbolic of psi. You can again do equations for, sine hyperbolic of psi, and basically try to get rid of the hyperbolic function. So what is x divided by t? That's just the speed of frame k prime as you measure in frame k, right? So x by t is just that speed. So I put x prime equal to 0. That means that there's no spatial displacement in the k prime frame, but there is some displacement in frame k. And so that displacement divided by the time is basically the speed. X by t is just the speed. So x by t is just v, which is the speed of k prime as measured by k, right? So that's just the speed between the two frames. So yeah, so instead of psi, you can just express everything in terms of this velocity, and it's just more intuitive because psi is an angle, and that's not very intuitive, but we kind of understand what v is, the velocity between frames. So it's always easy to put it in this form, and that's the standard form. So you end up with, you kind of get rid of psi here, and then you write the transformation in this form. So you get this same equation now becomes x equal to gamma. Gamma is the Lorentz factor. So gamma is just 1 over square root of 1 minus v square by c square. You've all probably heard about this. It's called the Lorentz factor, times x prime plus, now beta is v by c. So beta just tells you, beta and gamma tell you what is the relative velocity between the two frames, basically, right? So you get a transformation for x, transformation for time. Now again, nothing is changing along the y and z axis from the way we set up the coordinate system. So nothing is going to change on the y and the z direction. They remain the same. So this is called a pure Lorentz boost along the x-axis, right? So if the picture you need to have is, let's say you have a frame k prime. K prime is moving with respect to frame k with some velocity v. V by c is beta, and 1 over square root of 1 minus beta square is gamma. With those quantities given, this is how you would go from the primed frame to the unprimed frame, okay? And by symmetry, you can again write an equation where you basically go from the unprimed frame to the primed frame, and you just be an equation similar to this but with a negative beta, because the relative velocity is negative in this case. Okay, so some of the common concept, which again, for many of you this is just revision. The most famous of the consequences of this kind of geometry is, the first one is time dilation and the second is length contraction. So I'll just briefly talk about it just as a revision for you. So let's say you have two frames, you're in frame k, your friend is in frame k prime, and k prime frame is moving along the x-axis with respect to the k frame with some velocity v. And let's say your friend has a clock, and the clock is measuring some intervals, and the question is, what is the relationship between time in frame k prime and time in frame k, okay? Now, if you want to do that, then you want to have a clock which is at rest in frame k prime. Okay, so you get rid of that complication of space and time being coupled. So you just say that this clock is at rest. Okay, so I'm measuring the time at the same location. The clock is just sitting there ticking, so you don't have that weird problem of coupling between space and time. So let's say this clock is at rest. So between two ticks of the clock, it doesn't move, right? So dx prime, dy prime, dz prime is 0, and it measures some interval dt prime, right? And so again, now I'm going to just put in the Lorentz transformation. So c times dt, which was the second equation here in the Lorentz transformation, is gamma times c dt prime plus beta times dx prime. So we have just gotten rid of this. This is 0. The clock is measuring time ticks at the same place. So this dx prime is 0. Then you basically get dt is gamma times dt prime. So what does it mean? That means that this basically means moving clocks tick slower. So even though your friend measures an interval dt prime, to you, that interval is gamma times dt prime, right? So it's actually longer. You're going to measure a longer interval. So if your friend measures 1 and gamma is 10, let's say, then you're measuring 10, right? So to you, it looks up as though the clock is ticking very slow. That's why you kind of measure 10 units here, even though your friend measured just 1 unit, right? So to your friend, the clock seems like it's ticking at some rate. To you, it looks like it's ticking at a much slower rate. And so that's the basic idea here, that the moving clocks tick slower. And that's just called time dilation. Okay, length contraction. This is again a strange effect where the length of objects just are going to be different in different frames. Really weird concept. And again, I mean, this just comes out of the basic Lorentz transformations. We have the same setup in terms of the frames k prime. They're moving with velocity v, and now I put a rod here. So your friend has a rod which is at rest. Okay, in your friend's frame. And the question is, will you agree on the length measurement of a rod? Now, one thing to notice is if you want to measure the length of an object, then you basically have to measure the distance between its two ends at the same point in time, right? So let's forget about how you would set up this measurement. It doesn't matter how you want to set up this measurement. The principle is that you need to measure, to get the length of an object, you mark off one end, you mark off the other end of the object, and you measure the distance between the two. But this object might be moving, so you need to mark off the ends at exactly the same time. So for you to measure the length of the rod, you need to enforce dt equal to 0, right? That's the only way for you to actually measure the length of any object, is to measure the two ends at the same time. Again, you put in the first and the second equation we had for Lorentz transformation. Now we are going to say that dt is 0, right? So this equation must go to 0. Right, that equation is 0. So you basically get dt prime, which is the time interval between the measurements of the two ends in your friend's frame, right? So this, in your frame, you measure it at exactly the same time, but already from special relativity, we are not going to agree on time, right? Your friend and you are not going to agree on time. You have to go through that Lorentz transformation. So you get dt prime. Plug it back in this equation, and then simplify. You basically get L equal to L naught by gamma, where L naught is the distance your friend measures, right? So to you, the rod is appearing shorter. And so that's the second adage, which is that moving rods appear shorter, moving clocks tick slower, right? So that's length contraction and time dilation. Okay, now I want to, I guess all of this was known to you. So I want to do something which might be new for some of you, and that's the transformation of velocity. And the reason for why we want to look for velocity transformation will become obvious very soon. Again, we have exactly the same setup, right? We've chosen the axis such that the x-axis lie along the relative velocity. You're in frame k, your friend is in k prime, and k prime is moving with respect to k with that velocity v, right? So here are the equations again for the Lorentz transformations. And now I want to find the transformation of velocity. So what would be the definition of velocity in any frame? It's just the distance traveled by an object divided by time, right? So I'm going to say that let's say there is some object, it goes from one point to the other in some interval of time. And then I'm going to ask myself, oh, what's the velocity along the x-axis, let's say. Now, velocity along x-axis is just dx by dt, right? This is what you would measure as velocity. Now, that infinitesimal change dx, I can write in terms of the same infinitesimal quantities in your friend's frame, in the primed frame, and I can do the same for dt, right? So I do the same things, divide by dt prime, I get this equation, and so vx prime is dx prime by dt prime. So I'm going to get an equation where I have the velocity of a particle in my frame, and I have the velocity of the particle in my friend's frame, which is the primed quantity. And that's the relationship between the two. So if your friend measures this velocity for the same particle, you will be measuring this velocity for that particle. Okay, so far it's pretty simple. You just take differentials and try to, put everything in terms of the velocities. You do the same for y. I mean, you can pause the video and go through the algebra. It's quite trivial. Again, vy is y component of velocity, dy by dt. Dy doesn't go through any Lorentz boost because the velocity is not along that axis. Dt goes through a Lorentz boost. And again, you get an expression in terms of vy prime. And the same happens to vc. Okay, so that's how you would transform velocities, right? You can keep going like that. You could transform accelerations this way. But I want to use this to actually discuss a very interesting concept called the aberration of light. And the aberration of light basically is the idea that the direction in which light travels is not going to be the same in all inertial frames. So you can have a scenario where you and your friend are in different inertial frames. You say that the light is coming from some direction, but your friend just thinks it's coming from a different direction. And that is called the aberration of light. So all the angles are kind of, the angles are not the same, right? There is some transformation of angles, and that's why it's called aberration. It's as if there is a visual aberration of what is happening in front of you. And this leads to very strange effects, which we are not familiar with because we're not moving at these speeds. But you can have a scenario where you're moving at a very high speed and you're looking through, let's say you're going on a highway or something through a forest, and then you can have this strange situation where the entire forest kind of deforms. And that's why it's called an aberration, because it is like a visual aberration. Everything is deforming. Now, how would you do that? So for light, let's say now you're talking about, now we said velocities, right? So we said, let's say particles are moving and we're measuring their velocities. Now let's suppose that particle is light, right? So that particle is the photon. So its velocity has to be c in all the frames, right? That is one of the postulates of special relativity. So let's see what the consequence is. So for light, we're going to have v equal to v prime equal to c. Okay, so let's assume that beam of light is traveling in the xy plane without any loss of generality. Okay, and let's say it's traveling at an angle theta to the x-axis in your frame. And so you're going to say my vx is c times cos theta and my vy is c times sine theta, vz is 0. That's what you're saying, right? Now your friend says that beam of light is also traveling in the in your friend's xy plane, so x prime y prime. But now your friend is going to say that it's going at an angle theta prime. Okay, so you'll see that you're not going to agree with your friend on this angle theta. So your friend is going to say vx prime equal to c times cos theta prime, vy prime is c times sine theta prime, and vz prime is 0, right? That's what your friend is claiming. Now we take all of you can take this and put it through these equations which we just derived. So let's pick one, right? So let's pick the first equation. So you're saying, so you're going to replace this by v times cos theta. For your friend, it's going to be vx prime times, for you, this is going to be c times cos theta, right? Vx is c times cos theta for light. For your friend, this is going to be c times cos theta prime, right? And you have the equation for the aberration of light. You just get cos theta is cos theta prime plus beta, right? That beta comes from here. And then in the denominator, you're going to end up with 1 plus beta times cos theta, right? So you're going to end up with that in the denominator. Now, that's a very interesting equation. So let's say that your friend is actually moving close to the speed of light. Let's say, so the beta with respect to you. So let's say you're watching your friend in a different frame, moving very close to the speed of light. What does it mean? That this beta is basically going to be close to 1, right? So you're going to end up in a situation where the numerator is going to be cos theta prime plus, all some quantity close to 1, divided by 1 plus, some quantity close to 1 times cos theta prime. So this is going to end up being very close to 1, right? So you're going to get 1 plus cos theta prime, and then again 1 plus cos theta prime. And this quantity is going to be close to 1, which means that your cos theta is going to be equal to 1, which means that your theta is going to be pi by 2, right? You can have a large theta, but for your friend, all of that is going to be distorted. So your friend can have all of these different angles, and you're going to just measure cos theta equal to 1. So you're just going to measure theta equal to 0. Sorry, I said pi by 2, I think it's 0. Sorry, cos theta equal to 1 means theta equal to 0. So your friend can measure all these different angles. You're just measuring 0 angle in your frame. And that is the aberration of light. So you can have a scenario where, your friend is measuring all these different rays coming in different directions, but you in your friend's frame, but you just see everything coming from, close to theta equal to 0 because of this aberration. Now, again, if beta is very, much smaller than 1, then you can see that cos theta is equal to cos theta prime, right? So that's obvious. Now, I've just written a small code to actually, show you what it looks like in reality, the scenario I just described. So I've just assumed that the frame K prime is moving with velocity beta times c with respect to the frame K. Okay, so that's your friend's frame, K is your frame. And I've just said beta equal to 0.9, and I have drawn a few rays of light, let's say, which you see in your frame and which your friend sees in the K prime frame. So let's say your friend actually sees some kind of an isotropic set of rays which are going in all these different directions. To you, they're going to look as if they're all boosted in one direction. And that's basically pictorially telling you what I just said here. You can have all these different values of cos theta, but if beta is very close to 1, this ratio is always going to be close to 1. So you'll always measure theta equal to 0, right? And that's what you're seeing here. These are rays with all different values of cos theta, but for you, they're all concentrated along theta is equal to 0. And this would have profound consequences for all kinds of things. All kinds of things we're going to work out in this course, because if you have a particle which is radiating, and if the particle is moving relativistically, then to you, all that radiation is going to appear directed in a very narrow set of directions, right? As shown in this figure. Even though to the particle itself, the particle might, in its frame, the particle is radiating isotropically, let's say, or even with a dipole pattern, the sine theta pattern. But to you, it's going to look as if all of that radiation is kind of concentrated in like a very narrow forward cone, and you call that beaming. All that radiation is beamed in a certain direction. And again, that just comes from simple Lorentz transformations. You just find the equation for the transformation of velocity, and then you say what happens to light, right? So you just say that what happens to a particle whose velocity is always c in both frames. Yeah, and so that's the aberration of light. Well, I must actually mention something interesting here, at least for the astronomers, is you have to correct for this when you point a telescope, okay? And the reason for that is the Earth is going around the sun, right? We're going around the sun at 30 kilometers per second, roughly. The Earth is also spinning. So at the equator, the speed is about 1 kilometer per second, which means that if you have the coordinates of a star, which are, let's say, in the barycentric frame, so they're in a frame where they're in a frame which is the barycenter of the Earth and the sun, which is a very common way to express things. So we can all agree on measurements. And then you say, well, I'm going to go and point my telescope at that object. It turns out that you actually have to account for this aberration. And if you don't, you'll be off by, I think we'll do a problem, I might be wrong here, something like 15 arc seconds. So it's a huge effect. if for the astronomers, most telescopes nowadays will have a pointing accuracy of 1 arc second, right? So you can say this position in the sky will be there to within 1 arc second. That's like huge. It's an order of magnitude larger. So big effect from the aberration of light, just in practical matters of pointing a telescope at some object. Um, of course, once we talk about radiation from charges, once they're relativistic, the effect is going to be absolutely enormous. It's going to dwarf many other effects to the point that we're just going to say, oh, for a relativistic particle, this is generally true, because this effect of aberration is just going to be absolutely enormous for these particles.